Welcome to the second lecture on Module 6, Pre-stress Concrete, Design of Concrete Structures 2. I am Indu Geevar, Assistant Professor, Department of Civil Engineering, Rajagiri School of Engineering and Technology. Now the next problem. A rectangular beam of cross-section 250 mm by 400 mm, pre-stressed by 50 numbers of 5 mm diameter bars, located 60 mm from bottom of the beam, and 3 numbers of 5 mm diameter bars located at 40 mm from top. So this will be the cross section of the beam 250 by 500, 400, and the three numbers of pre-stressing bars are located 40 mm from the top, and 15 numbers of pre-stressing bars of 5 mm diameter located at 60 mm from the bottom. Now firstly we have to find the centroid of the tendons. For that, you can use a normal centroid formula. Let the centroid of the tendons be at a distance y from the bottom. Then we can say that the area of the total pre-stressing force AP, pre-stressing tendons, into y will be equal to AP1 into Y1. AP1 is the area of the pre-stressing steel in one layer. Okay, so let this be the area and the distance be Y1. So this is Y1. And AP2 into Y2. So AP2 will be the area of pre-stressing steel in the second layer, and Y2 will be the distance from the reference line. So this will be the Y2. Since here we have used 5 mm diameter for all the steel, the area of one steel will be pi by 4 into 5 square. So it will be same for all the steel. So we just need to use the number of bars. So the total number of bars is 18. 18 into y will be equal to 15 is the number of bars in layer 1. 15 into 60 is the distance from the as shown in the figure, and plus 3 is the number of bars in the top layer into the distance y2 will be total depth 400 minus the 40 mm. So we get a y bar of 110 mm. That is, you can represent this entire steel assumed to be located at the CGS at a distance of 110 mm from the bottom. Now to find the eccentricity is the distance from the centroid of the cross section to the CGS, that is the centroid of the tendons. So we now located the centroid of the tendons, that is at 110 mm from the bottom, and we know that the centroid of the cross section will be at d by 2 distance for a rectangular section. So eccentricity can be calculated as d by 2 minus y, that comes to 90 mm. So this distance will be 90 mm. Now in the question it is given that the initial stress in steel is 1000 MPa. So stress in steel will be transferred to concrete as compression. So the force in steel will be the stress in steel into the area of steel. So finding the pre-stressing force, initial pre-stressing force will be stress into the area of the pre-stressing steel. So that area of the pre-stressing steel will be the total number of bars, that is 18 bars, into the area of 1 bar will be the total area of pre-stressing steel into the stress. Stress is 1000 MPa is given to you. So we get a value of 3,53,429 newtons. This is the initial pre-stress. So I already mentioned that there will be some loss of pre-stress after some time. So we have to consider the loss also, that is given here in the question. Assume loss in pre-stress to be 10%. That means the net pre-stress available will be initial pre-stress minus the 10% of the initial pre-stress. So that comes to 3,18,086 newtons. This is after losses. So this is the pre-stress we have to consider for the subsequent calculations. Now we obtain the pre-stressing force and the eccentricity of pre-stress. So we can calculate the stresses at the cross section. The question is to find the bending moment the section can resist and at service. And the maximum allowable compressive stress is given 16 MPa, and no tension is allowed in the cross section. Now the section properties, the area of cross section A and Z can be calculated. From that we can calculate P by A, it comes to 3.18, and P by Z, it comes to 4.29 the bottom, plus 4.29 at the bottom and minus 4.29 at the top. Now M by Z we don't know, we have to calculate the M. So the net stress at the top will be 3.18 minus 4.29 plus m by z, and the net stress at the bottom will be 3.18 plus 4.29 minus m by z. Now the maximum compressive stress will be at the top at surface, so that should be less than or equal to 16 MPa, and the minimum compressive stress will be at the bottom at surface, and this value should be greater than or equal to 0 for no tension condition. Now using the first condition 1, you will get an m should be less than or equal to 104 kilonewton meters, and from the second condition, we get an m of less than or equal to 49.8 kilonewton meters. So from these two conditions, we get that the safe bending moment should be less than or equal to 49.8 kilonewton meters, because here 104 is greater than 49.8. So the net safe bending moment will be 49.8 kilonewton meters. Now we have to calculate the safe live load on the simply supported beam subject to UDL. So we know that the bending moment is given by W L square by 8. So W is, we don't know, we have to find out. L is a span that is given as 6 meters, 6 square by 8, and this value should be less than or equal to 49.8. Solving this, the W should be less than or equal to 11.06 kilonewton per meter. Now this includes the dead load also. The question is to find the safe live load. So dead load we can calculate as 25 unit weight of concrete into the cross-sectional area, that is 0.25 into 0.4. That comes to 2.5 kilonewton per meter. So the live load can be calculated. Live load will be equal to the total load minus the dead load. So that comes to 8.56 kilonewton per meter. Coming to the next problem. An unsymmetrical I-section beam is used to support a live load of 2 kilonewton per meter over a simply supported span of 8 meters. The effective pre-stressing force of 100 kilonewton may be assumed at 50 mm from the soffit of the beam at midspan. Estimate the stresses at the midspan, at transfer and service. So there are two stages of checking for stresses, that is at transfer and at service. At transfer, it is soon after the pre-stressing is applied. Here we need to check only for dead load and not live load. At service, we have to consider all the cases: pre-stressing force, dead load and live load. First step is we have to calculate the centroid of the cross section. So for that, we know the centroid of a rectangle. So from using that, we can find the centroid of this unsymmetrical I-section. Let the centroid be located at a distance of y bar from the bottom. Then the y bar can be calculated using the centroid formula, y bar equal to sigma ai yi bar by sigma ai. For this purpose, let us divide the area of this cross section into 3 rectangles as shown. And let the first rectangle be the bottom rectangle. That area of that rectangle will be 100 into 60. That comes to 6000 millimeter square. And CG of this rectangle will be exactly in the middle. And this distance will be y1 bar. So y1 bar will be 60 by 2. That will be 30 mm. Now considering the next area, A2 will be area of the middle rectangle. That will be 280 into 80. That comes to 22,400 millimeter square. And CG of the rectangle will be middle of this rectangle. So this distance will be y2 bar. That will be 60 plus 280 by 2. It comes to 200 mm. Considering the third area, the CG of this area will be in the middle, and this distance will be the y3 bar. And since it's the middle, this distance will be 60 by 2. That will be 30 mm. And the total height we know is 400 mm. So 400 minus 30. So y3 bar will come to 370 mm. And the area of this rectangle A3 will be 300 into 60. That will be 18,000 millimeter square. Now let us calculate the total area, that is sigma AI. That will be 6,000 plus 22,400 plus 18,000. That comes to 46,400 millimeter square. Now let us use the equation of centroid. Y bar equal to A1 Y1 bar plus A2 Y2 bar plus A3 Y3 bar divided by the total area. Y bar comes to 244 mm. Now we got the centroid of the section. It is located at 244 mm from the bottom. Now next is we have to calculate the section modulus. This is to calculate the stresses, because stress is equal to stress due to the bending moment will be m by z. So z will be is equal to the section modulus will be equal to I by yt. For the top it will be yt, and for the bottom it will be yb. So here yb is the distance from the centroid to the bottom. So this will be yb, and the remaining distance will be the yt. That will be 400 minus 244 comes to 156 mm. Now we have to calculate the moment of inertia I. For that again we will divide it into rectangles and we will add the moment of inertias. So the moment of inertia will be I1 plus I2 plus I3 for the three rectangles. We are calculating the moment of inertia about the centroidal axis, horizontal axis. So we have to use the parallel axis theorem to shift the axis. So for the rectangle, the moment of inertia is 1 by 12 PD cube. That is 1 by 12 into 100 into 60 cube. Now we have to shift it to the centroidal axis. For that you have to use the parallel axis theorem. So plus AH square. So here this will be H. So area into H square. So H here will be 244 minus 60 by 2. So AH square will be 100 into 60 into 244 minus 60 by 2 whole square. So we get a value of 276.576 into 10 raised to 6 millimeter raised to 4. Considering the second area, here 1 by 12, 80 into 280 cube. Here area into h square will be, area will be 280 into 80. Here h will be the distance of this CG of this rectangle to the centroid. So this will be the distance. So CG of this rectangle, this distance will be 200 mm. So the distance between the CG and the CG of this rectangle will be 244 minus 200 square. And it comes to 189.713 into 10 raised to 6 millimeter raised to 4. Now considering the third rectangle, the CG about the moment of inertia about its own axis will be 1 by 12 into 300 into 60 cube. Now we have to shift it to the centroidal axis. For that you have to use A into h square. Here A will be 300 into 60 and the distance will be this distance. This will be h here. That comes to 156 minus 60 by 2. So this will be the equation. So you get 291.168 into 10 raised to 6. Now the total moment of inertia will be I1 plus I2 plus I3. That comes to, now we know that section modulus set T will be equal to I by YT. That can be calculated. YT we know it is 156 mm. That comes to 4.8555 into 10 raised to 6 millimeter cube. Similarly, set B will be I by YB. That will be I by 244. That comes to 3.1043 into 10 raised to 6 millimeter cube. Now next step is to find the eccentricity of pre-stress. So we know that it is given that the pre-stressing cable is located at a distance of 50 mm from soffit. That is 50 mm from the bottom. Eccentricity will be the distance between the CGC and the CGS. That is the centroid of the cross section of concrete and the centroid of the cross section, centroid of the tendon. So this will be the distance given by eccentricity. So eccentricity will be equal to 244 mm minus 50 mm. That will come to 194 mm. Now let us calculate the stress distribution. First at transfer. At transfer there will be pre-stressing load and the dead load. Now due to pre-stress there will be a stress, axial stress due to pre-stress will be P by A. Now the pre-stressing force is given as 100 kilonewton, that is 100 into 1000 newtons divided by area. Area we already calculated. That comes to 2.16 MPa. So this will be 2.16 MPa. Now due to the eccentricity of pre-stress there will be a hogging moment. Due to that there will be a bending stress PE by ZT at the top and PE by ZB at the bottom. Here you have top tension and bottom compression because it's a hogging moment. So calculating PE by ZT, we get P is 100 kilonewton into the eccentricity is 194 mm divided by ZT, we get a stress of 4 MPa. So this will be 4 MPa. Now the bottom stress will be P by ZB. So substituting the values, we get a stress of 6.25 MPa. So this will be 6.25. Now due to the loading, we need to take only dead load for calculating the stress transfer. So it will be MD by ZT and MD by ZB at the bottom. So at top it will be compression plus and bottom it will be tension minus because it's a sagging moment. Now the bending moment due to the dead load will be WL square by 8. The W will be the dead load on the beam. So the dead load will be 25 unit weight of concrete into the area in meter square. So we get 1.16 kilonewton per meter. So substituting the values WDL L square by 8. So it comes to 9.28 kilonewton meter. This is the bending moment due to the dead load alone, maximum bending moment. Now calculating the values, top bending stress will be 1.91. So this value will be 1.91 and the bottom bending stress will be 2.99. So the net stress at the top will be 2.16 minus 4 plus 1.91, that comes to 0.07 MPa, and the net bottom stress will be 2.16 plus 6.25 minus 2.99, that comes to 5.42 MPa. So the final stress diagram will look like this, with stress at top equal to 0.07 MPa and stress at bottom will be equal to 5.42 MPa. Now next is the stress at service, which includes pre-stress, dead load and live load. Here also the stress distribution will be similar to the earlier case. Only thing is that here the bending moment will be the total bending moment and not the bending moment due to dead load alone. So here we have to consider the bending moment due to dead load and live load. To the pre-stressing force, all the stresses will be same. We calculated this is 2.16, this is 4 and this will be 6.25, which we have calculated in the. Now the total load on the beam is the dead load plus live load. Dead load we already calculated 1.16 plus 2, that comes to 3.16 kilonewton per meter. So calculating the total bending moment, it will be WL square by 8 at the middle span. So that will be 3.16 into 8 square by 8, that comes to 25.28 kilonewton meter. Calculating the bending stresses, M by ZT and M by ZT will be equal to 5.21 MPa at the top and M by ZB will be equal to 8.14 at the bottom. So the net stress at the top will be 2.16 minus 4 plus 5.21, that comes to 3.37 MPa, and the net bottom stress will be equal to 2.16 plus 6.25 minus 8.14, that comes to 0.27 MPa. So the final stress diagram will look like this, with top stress as 3.37 and bottom stress as 0.27. And from this, it's also understood that there is no tension within the cross section. The entire cross section is in compression, both in service and at transfer.